Good morning. I am Yashika Sharma, MSc Chemistry, second year, CML 661, solid state chemistry student. Today I am going to discuss how we can identify the point group of a given crystal system. It can be complex to determine the point group of a given crystal system if we jump from the external morphology of the macroscopic crystal level to the point group, which is generally defined at the unit cell level. It can belong to any of the seven crystal system, that is the arrangement of the molecule in the crystal, and its symmetry may be expressed by using the seven crystal system that are available. In this, I have used a schematic framework of going from the crystal structure to the crystal system to the point group. It is beneficial to determine the crystal system from the given crystal's external morphology because the crystal system is valid at the unit cell level. And as the unit cell is the smallest repeating unit of the crystal, which builds the entire crystal structure when it is repeated in three dimensions. So anything which is true at the unit cell level is basically true for the entire crystal. So, in this slide, we can see the photos of the given crystal structure from different angles. It can be clearly seen that the external faces are inclined to each other at some angles, but it has a parallel top and bottom face which do not have any intersection with each other. We can see that the side faces are intersecting and inclined to each other at some angle, but the top and the bottom face are parallel to each other. We can say they are equivalent set of parallel planes. And in this picture we can see the top face and the side face which are emerging from each side of this square top face. And the top face need not to be always square because the sides of these can be of different lengths. Also, a chart is shown illustrating the seven crystal system and the example of their common forms, which is visual example of their characteristic shapes. What does it mean? It means that a crystal showing a particular crystal system can have external morphology of any of these shapes, which means that if a crystal is showing cubic crystal system, then it can have its external morphology in any of these shapes. Tetragonal, it can show its external morphology and external shape in any of these shapes. The 2D diagram of the same has been drawn using paint. The side tilted view, that is this view, the side tilted view actually shows that the top face and the bottom face is having four sides, and from each side inclined planes are coming in outward direction, reaching the middle, that is this, the middle intersection of the two planes turns inward and meets the bottom plane, which is equivalent to the top face, which means that the planes that is coming from the sides of the top face into the bottom reaches the middle in outward direction, and then from the middle it moves in inward direction and meets the bottom plane. And as we can see from this we can see that this exact external morphology is shown in the crystal form or structure having a monoclinic crystal system. That is, monoclinic crystal system can describe the entire symmetry of this crystal system. I mean this crystal structure. Establishing that this is the monoclinic crystal system, let us analyze the crystal facets. As we have already seen that the top face, this is the picture from the top view of this picture, the crystal which is given to us. The top view shows that the top of the crystal face and the bottom, which is right below this, are equivalent plane. If it is 110, that too will be 110, 110, or 1 bar 00 actually, because these are equivalent planes. We can see that the side planes coming out from the opposite edges of this top face, these are non-equivalent. 1 1 bar 0, 1 1 1 1 0, and these two planes are inclined at some angle to the top face. Similarly, these two planes also are non-equivalent planes coming out from the opposite edges of the top face. These then now moving outward, if we see from top, from in the bottom they are going inwards and then meeting at the bottom face. Actually, these facets indicate how the crystal grew. Slow growing planes become large flat faces while the fast growing plane may vanish. So the facet size and orientation show growth direction and stability. This facet diagram shows the crystal system crystallizes in monoclinic crystal system. The crystal axes ABC are all of unequal length, and the angle beta between A and C is slightly greater than 90 degree, giving the crystal a tilted prismatic shape. To see the beta angle, we can see the plane A, that is 110, and the plane C, which is 001. Now, if we can make like a crystal system diagram, this will be B, this will be C, and this will be A. So, sorry. This will be A. So, if we consider 110 plane, it will be like this, cutting the A axis in one and parallel to B and C. And the CC001 C plane will be cutting C axis and not with any AB axis. So if we shift the origin from here to here we are shifted. This is C, this will be A, and this will be B, right? So the angle between these planes, that is 110 and 001, this angle will be beta because it is between C axis and A axis, and it is clearly shown that 110 and 001 is not 90 degree, it is greater than 90 degree. Like the top plane is like this, and this like this, like this, it is like this, more than 90 degree. No, this is 90 degree and it is like this, more than 90 degree. So this is again a characteristic trait of monoclinic. Also, the presence of other facets like 110, 101 and 001, these all reflect tilt and they are not perpendicular, confirming the other symmetry rather than cubic, tetragonal and orthorhombic. Now, as the crystal which was given to us was a sucrose crystal system, I have taken the XRD data of a sucrose crystal, which shows peak at plane 2 1 minus 1, 0 2 1 and 1 1 0. These are the intense peak of all the peaks that are available. The reflection of the XRD lines from these peaks represents that these are the direction along these planes have the growth of the molecules of the crystal is majorly in this direction, that is the direction along these planes. Now, of the 3D pattern of the molecules of sucrose, this portion is taken to determine the blue shaded region, that is 110, 2 1 minus 1 and 002 planes, which have the growth of the molecules in their direction, which is reflected in the outer morphology of the crystal. As we can see that the 2 1 minus 1 plane and the 0 0 2 plane, 0 0 2 plane being the top plane, and the 2 1 minus 1 is an inclined plane. So these two planes are not at 90 degree, but rather than greater than, somewhat greater than 90 degree. They are if we place them together on edges, they have an angle greater than 90 degree. So this also shows us that the crystal symmetry is of monoclinic. Now, so now, having established that the crystal system, crystal structure which was given to us belongs to the crystal system having monoclinic symmetry. So of the 32 crystallographic point group, the point group that belongs to crystal system of monoclinic are 3. So this narrows us down to the point group 3. The crystal given to us can have a 3 point group, either 2, which is given here 2, 2 by M and M. Now, very interesting point, that the crystal which was given to us was a sugar crystal, and it was made up of sucrose molecules. So a sucrose is a chiral molecule, which means that as it was a chiral molecule, it means that it cannot have the point group which inverts the symmetry of the molecule which is present inside it, that is the sucrose molecule. So we know that the mirror plane, for the mirror plane to exist, there has to be a enantiomer. Like uh, if we have a molecule like this in plane, one is coming out of the plane and other is going inside the plane, like this. If a mirror plane exists, if it is present on one motive and the mirror plane exists, which means that it is reflected like two planes in this bond is reflected here by the mirror plane, and this bond here, two in plane, one coming out of plane reflected here and other coming inside the plane, going inside the plane here. So if we see that this is the R configuration of the molecule, this turns out to be the S configuration of the same molecule. So if the molecule is chiral, we have seen that it can crystallize only in the Schonke space group, which do not have any symmetries which can invert its configuration, the molecule's configuration which is present inside that system. So as we have seen, for the mirror plane to exist, two enantiomer has to be possible, and if a molecule is chiral, its crystal system have to be chiral, and it contains either S or R enantiomer, not both. So the mirror plane cannot exist because the R reflection S will not be present, only RR will be present. So the symmetry operation which can preserve its configuration, that is the rotation and translation, only that can be present, but symmetries like inversion center and the mirror plane cannot be present, because for that two enantiomer has to be present, but as the system is chiral, only one enantiomer is present in our crystal system, so it cannot have 2 by M and M, because it contains mirror plane which is the configuration inverting symmetries. So this narrows us down to only the point group which is possible for the crystal is 2. So due to this point group chirality of the molecule which is present inside the system, crystal system, and the crystal system monoclinic. So from going from the crystal, determining from the crystal structure to the crystal system to the molecule symmetry which is actually present inside the crystal system, we have concluded that the crystal that was given to us has the point group present as 2. So here I have shown an animation depicting all the possible point group that a monoclinic system can have. We can assume it is a random monoclinic system. It can have two axes, two-fold rotation axis which is passing through the center, and the two plane which was depicted as this, the two plane. depicted. 2 by m means the twofold axis of rotation is here and perpendicular to the twofold m is present, and for m to exist, the molecule present here, its reflection should be present at this position, and the reflection inverts the configuration, which means if R is present here, R molecule inside the crystal system, the S molecule has to be present at this position, which is not possible because our crystal system is chiral and it can only have one of the enantiomer, either R or S. So the mirror plane cannot be present, but twofold axis can be present. Here the unit cell system is shown by this picture. This is the A axis, this is the C axis, and we can imagine the B axis, which is perpendicular to the screen, going inside the screen like this. If this is the screen, this is the twofold rotation which is coming through it. So this is the twofold rotation. So we can see, if we rotate twofold around the from the center of this unit cell, if we rotate 180-degree, this molecule comes here and this molecule comes here, which generate the new system, which is exactly same as the original system before the rotation. So that is why our crystal system have the point group present as 2, because it is a monoclinic crystal system, and second, it is a chiral molecule containing crystal system. Thank you. So from this exercise we have learned how to find the crystal system of a given crystal structure and going to the point group of the crystal, visualizing how the atom in the crystal depicts the symmetry of the crystal and influences the way it forms in the 3D space. Thank you.